Great morning, everyone. Welcome aboard. Let's jump right into it with some new tests for convergence of series. We've already seen geometric series, p-series. We've seen the integral test. Now we're going to add the comparison tests. And in this video, we're going to look at the direct comparison test, which is exactly the same as the comparison test for improper integrals, just instead with series. And in the next video, we're going to look at the limit comparison test, which is a little more applicable. It's more robust. It's in fact a little easier to use than the direct comparison test, but requires a little bit different way of thinking. And we hopefully will understand that better when we see some examples of when the direct comparison test fails. So let's start right off the bat with the direct comparison test. Notice that I've already specified that this lecture, meaning the two videos made from this, the series have positive terms. And I'm just going to call them A and B. A is going to be the series you start with. So A is going to be the starting series, the tested one. So it's going to be the series we're testing. And Bn is going to be a comparison that you provide. Just like in the integral case, you have to actually provide another series to compare to the one that you have. And usually it's straightforward as to which series to compare it to, but you still have to be a little clever sometimes. So, the direct comparison test, so theorem. The direct comparison test, sometimes just called the comparison test. Alright, the first one, let me just put a line under here. If I start with my comparison series, now remember I'm testing A and I have B and I provided you with B. If B is convergent, so if the piece that I'm providing is convergent and AN is sitting below BN for all n, aka my series that I'm testing is quote-unquote smaller than the series that I'm comparing it to, in the sense that each of the terms are smaller at each index. So if I have a series which is convergent and I have a series that's sitting below it, it has to be convergent as well. It can't go up to infinity because it will hit that convergent series that is sitting above it. So if I have a convergent series and my testing one is underneath it, then AN is also convergent. Conversely, if your Bn is divergent, so you have a series that's going up to infinity, and the series I'm testing is bigger than it. So AN is bigger than BN. Well, if I have something that's bigger than an infinitely large quantity, it also has to be infinitely large. So if AN is bigger than a divergent series, it has to also be divergent. So AN is also divergent. Great. Notice that the first part of this, Bn is convergent, so AN has to be convergent. It doesn't say anything about Bn being convergent and having A be bigger than B. So if your comparison series is convergent, you're only going to be able to say something if the series you're testing is below it. If the series is above it, it can be doing whatever it wants. It could diverge for all you know. But if you have a convergent series that you're using to compare, and you have to have your tested one underneath in order to draw a conclusion from this test. So let us look at some examples. So example, this series here, n minus 1 over n cubed plus 1. So I look at this series and I see an n on the top and I see an n cubed on the bottom. And I'm oddly thinking, this looks a lot like 1 over n squared. Is it less than 1 over n squared? Is it more than 1 over n squared? Well, you just do the comparison. You start with your fraction, and I notice that I'm first going to compare it to this. Which of these two is bigger? Well, we know that fractions that have bigger numerators are bigger. So n is bigger than n minus 1. So this fraction is, the right-hand one is bigger than the left-hand one. Then I also have n over n cubed. And we also have this inequality here because the denominator for n over n cubed plus 1 is bigger than n cubed. Bigger denominator is a smaller fraction. And n over n cubed is 1 over n squared. So my series n minus 1 over n cubed plus 1 is smaller than 1 over n squared. I do know that the series 1 over n squared is convergent because it's a p-series with p equals 2 bigger than 1. So that's a convergent series. So my series is smaller than a convergent series. So by the comparison theorem, or comparison test, n minus 1 over n cubed plus 1 also converges. All right, wonderful. Let's look at another example here. Let's look at one that diverges. 1 over root n minus 1. So I'm just going to start naively doing some comparisons and seeing what happens. I immediately see 1 over root n is going to be my target here, my goal, the series to which I want to compare this. And I know that root n minus 1 is a smaller number than root n. And smaller numbers, smaller denominators, make bigger fractions. So we have this inequality. But 1 over root n is the same as 1 over n to the 1/2. So the series 1 over n to the 1/2 diverges. It's a p-series with p equals 1/2, less than or equal to 1. All right? So my series that I'm testing, 1 over root n minus 1, is bigger than a divergent series. It's bigger than an infinite quantity. So by the comparison test, my series has to diverge. There's no other option. It's bigger than something that diverges. Notice that I am starting with what I'm given. I'm transforming it into something. Then I'm making a statement about a comparison series. And then I am clearly saying that I'm using the comparison test or comparison theorem to make a conclusion about the convergence or divergence of this series. On a test, I'm not really marking 5 points for the word convergent or 5 points for the word divergent. I'm marking all of the logic, making sure you check all the assumptions, in particular for something like the integral test, which has a lot of conditions, making sure that you're using the premise of the test properly to reach the proper conclusion, like I'm doing here. All right, one last example, one that's not a p-series. All right, let's do a geometric series. Ish. 9, to the n over 3 plus 10 to the n. I'm seeing these numbers to the power of n, and I'm seeing one on the top and one on the bottom. To me, that's yelling geometric series comparison here. And when I start writing out this fraction, 9 to the n over 3 plus 10 to the n, and I want to compare that directly to something that is purely geometric, not just something that looks geometric, but purely so, I know that the left-hand side here, 3 plus 10 to the n, that's the denominator. That's a bigger denominator, so that's a smaller fraction. And you see where this is going already, because 9 to the n over 10 to the n is 9/10 to the n. So my series is smaller than that geometric series, 9 over 10 to the n. This geometric series that I'm smaller than is convergent, because it's geometric with its ratio equal to 9 over 10, which is less than 1. In fact, I could write it's 1 over this, the value of this series is 1 over 1 minus 9/10. I don't care what the value is. These tests are about convergent or not convergent. Usually you don't care what the value of the series is in this case. All right, so my series is smaller than a convergent series. So my series has to be convergent. It's stuck underneath a finite sum, or finite series. So by the comparison test, this series also converges. 9 to the n over 3 plus 10 to the n. Very nice. Very nice. Before we end, I want to do a non-example. Non-examples are things that almost work but don't quite. So let me look at 1 over n plus 1. Now you look at that and you say, well, that looks a lot like the harmonic series, 1 over n. So I'd start trying to compare these things. 1 over n plus 1 and 1 over n. And I go, okay. Well, 1 over n plus 1 is smaller because it has a bigger denominator. Cool. So I have this series, in some sense, is smaller than that series. This series diverges because it's a p-series with p equals 1, the harmonic series. So what I've said here is that my series is sitting below an infinite quantity. That's not the way the comparison works. I either have to have my series sitting above an infinite quantity, so it gets pushed up, or my series has to be sitting below a finite value so that it gets stuck. The comparison test does not help when I determine, as I have here, that my series is sitting below an infinite quantity. That's completely unhelpful. So the comparison test is non-conclusive in this situation. If my series was bigger than 1 over n, sure, I could say that 1 over n plus 1 was divergent, but it's smaller. So can't use the comparison test. We will learn how to test and prove that this is a divergent series in the next video, where we do the limit comparison test.